Hi, Armando. Good to see you.
Good to see you.
Yeah. How about using the large language model for the conceptual reasoning in the formation of these types of experiments? You know, if you want to start to talk to it about how it could come up with representations, have you tried that?
So, what kind of experiment, are you thinking about?
I mean, even conceiving of the paper itself. I mean, there was some spark of creativity in designing the experiment. If you were sitting down and said, you know, has somebody tried this before? What do you think about this? Could you get that kind of bootstrapping in that conceptual domain of the experiment itself?
So, I think you can get a lot of help, right? So, for example, some of the things that the models are extremely useful for is in, you know, getting a broad sense of the research that has been done in a particular space, right? And helping you identify what are the gaps in our understanding that still have to be addressed. Now, when it comes to experiment design, there has been some interesting work on using AI more broadly for experiment design based on models, building models based on our understanding of that domain and being able to generate alternative models, for example, that are all consistent with our understanding of the domain and being able to then come up with experiments that tease out the differences between those models so that you can tell which of them actually corresponds to reality. I think building on the existing infrastructure to create tools that are very useful on particular domains is I think, actually a really interesting and powerful research direction. Just having the model sort of in an open-ended way say, hey, what's an interesting experiment to run in the space of LLMs for code, that I would be much more skeptical.
Thank you.
Mm-hmm.
Not my field, so maybe a naive question, but a lot of languages like Python and C, stretching all the way back to Fortran, have very common structures, you know, do loops, branches, stuff like that. What about something like Perl, where you're talking about, you know, extremely complex syntax matching? Do language models handle that sort of thing very well?
So Perl has the advantage that it has, there's lots of Perl out there in the world, right, that the models have been able to look at. There has been a lot of research recently on what are called low-resource languages, right? What does it take to get these models to actually work well on low-resource languages? And that is actually one of the challenges that we talk about in our survey. There is still a big gap between the capabilities that you have in popular languages like Java and Python versus the capabilities that you have in very low resource, very specialized domain-specific languages. And there's a lot of research right now trying to help bridge that gap by bringing in more explicitly codified knowledge about, for example, the syntax of those languages, right? So that they don't trip up with quirky syntax that even when the model might know at a high level algorithmically what the solution looks like, but they often trip on the syntax when it comes to this low resource languages. We've also done some experiments in our lab looking more broadly at the abstract language learning capabilities, right? And to what extent do these models exhibit more abstract language learning capabilities when it comes to things that they've truly never seen before. And it turns out that even the most powerful reasoning models today just don't do very well on things that truly look very different from things that they've seen before.
Hi, thanks for the great talk. I think Gen AI and LLMs have made it possible for us to convert legacy applications much better in the code conversion part, and we are living in an era when that's possible of taking like millions of lines of code from legacy apps and modernizing them. The challenge we have found is mostly in catastrophic forgetfulness of when you take a large abstract syntax tree and make it out of a large code base and try to convert it or migrate it to a modern platform. And that's been a bane of existence, even with the larger context windows. Do you have any neurosymbolic tricks or techniques which you would recommend to address these issues?
So this is actually a very challenging problem and one that is getting a lot of attention. One thing about when you're talking about translation or migration of code is that doing it for very self-contained pieces of code, there's a lot of symbolic reasoning that you can bring to bear when it comes to do this, right? We have lots of tools to help you identify semantic differences between different pieces of code. The big challenge comes when, just like in any translation, there's important differences between what you can do in one language and what you can do in another language, right? The code in one language uses some library that doesn't exist in the other language, right? So you have to replace it. You have to find the right replacement, and oftentimes there might not be one library that does exactly what this old library did. You have to piece it together from bits and pieces of functionality from other languages, right? And suddenly you now have the full complexity of the program synthesis problem, even though you think that you're just translating, right? And this is why, even before LLMs, when people try to use more compiler-type techniques to translate from one problem to the other, this is where a lot of those techniques would really trip, right? When it comes to those pieces of code that are just not directly translatable from one language to the other.
So in one of the examples that you shared about coding, you draw like a couple of nodes referencing to how interpreter would evaluate the code. Is it more of like grounding the neural network and adding that information about the environment with the question that you ask the LLM so that it does not hallucinate and like limit it? Like, is that the goal here?
So there has been a lot of work on doing that sort of thing, right? And things like providing debugging information to the LLM, for example, so that it has that additional context. Usually, though, when you're doing purely static analysis, you just don't have that dynamic information, right? And so what you have to do is approximate it by looking at what other pieces of code are doing, right? And it's in that process of approximation that you have to make all of these decisions about what information is OK to lose, what information is not OK to lose, what information can be aggregated into a more summarized form, and what information just has to be kept concrete in order to answer your particular question. And that is where a lot of traditional program analysis end up losing much of their precision, right? And getting some help with that process. That's what we're really trying to do, leveraging that broader knowledge of the world that's embedded in the model.
And I can understand it for like coding, like you can control the environment per se, but like what about like and beyond, like all the other out of the domain topics? Like actually yesterday itself I asked one of the professors a question about like neurosymbolic versus whatever topic they were teaching, and the answer was like search can do this. Like if a model does not know something, just go and search for it. Like that's a capability for that. So how do you think about like domains apart from coding?
So that's a really good question, right? And one of the things that we really like about code is that it's not just a mean to build software. It's this very precise way of representing algorithmic concepts. And so, for example, one direction that we've been exploring fairly aggressively in recent years is the use of code as a representation outside of the software engineering realm, right? Whether you're talking about a robot, for example, trying to create a model of the world and of how the world is going to react to it, right? You can represent that model with just a blob of neurons, but you can also represent that model as a piece of code that you can run and that you can analyze using all the software analysis tools that we have available to us. And so when you do that, you actually gain a lot of capabilities relative to the purely neural representations, right? And we've actually been exploring sort of hybrids of the two, right? Because there are some aspects of the world that are just too messy to represent precisely with code, where the neural representation really is the best way to represent them. But you want to be able to have these hybrid representations that then you can reason formally about, right? And so now, leveraging the ability of LLMs to generate those models and to generate that code to be consistent with its observations about the environment, for example, it's a direction that we're very excited about.
Thank you.
All right, fantastic. Thank you very much, Armando. We're at the top of the hour, and we're going to move on to the next speaker. And as you're breaking down and Charles is walking up, you said something about LLMs and I don't know how I'm going to remember. With logical reasoning. And I remember Daniela showed me a video recently of a robot, and she said to the robot, "Can you water my plant? Water the plant." And the robot went and watered the plant. And then she said, "Can you water my friend?" And the robot went to water the friend. How do you build that logical reasoning into an LLM?
I mean, that's one of the big open questions in this space, right? You want to be able to rely on the kind of very crisp logical reasoning that we can do mechanically very, very well and very precisely. But you also want to avoid the kind of problems that people used to have when they built systems based purely on logic, right? Where it was very difficult to encode all the knowledge in the world in this symbolic form, right? And one of the things that we gain from the language models is this ability that they do have a lot of these background knowledge, right? And in fact, if you were to explicitly ask the model, hey, is pouring water over your friends a thing you do in polite society, it would probably tell you, no, that is not something you do, right? So it has that knowledge. It just doesn't have that ability to make those connections in a logical way, right? And I think that's one of the interesting directions here of how do you combine those two.
Great. Thank you very much, Armando. And yes, thank you very much.
Thank you, everyone.